Hey everybody, it's Wednesday, October 14th. As you can see here in the aim today, our goal for this video is to talk about how we can basically apply our understanding of gravitational acceleration to solve problems. Now, I'm sure I mentioned this before, but in many of the years past, after the kids finish taking the AP test, they often tell me they don't pick up their calculators all that much. The AP test really does not include many calculations where you're just going to be given a set of variables, plug them into an equation, and solve it. Even some of the more complicated problems that we've done so far this year, like the chase problem, they're not going to ask you to solve the whole thing out necessarily, as opposed to describing how the whole problem works. And so today's video is really going to focus much more on the style of question that they ask on the AP test. Now, I think it's certainly the case that it is really good practice for how to think about these problems to just actually solve them out and see what you get for the answer and start to notice some of the patterns. But the style of thinking that you have to do in explaining a lot of these problems is going to be shown here in this video today. So yesterday we talked about free fall and objects thrown straight up in the air. And despite the fact that those are two different problems, what is similar about them is that they both involve objects accelerating due to gravity. And so traditionally, while we think of only the first kind of problem, like just an object being dropped, as a free fall problem, they are technically both free fall problems because they both involve objects having only one force acting on them, and that force being the gravitational force from the Earth. So for today, what we're going to focus on is what I'm going to refer to as proportional reasoning. If you remember the first video I ever did for this course this year, we talked about the science practices that the College Board lists in its curriculum guide for this course. And only one of them was about using math. The rest of them were about using models and coming up with arguments and explanations to basically answer a problem that way. And so the way we're going to do that for today is by using what we're going to refer to as proportional reasoning. So we're going to say a couple of things about this, and then we're going to show how this works and how you'll use this. So the first thing we can say about this is we use proportional reasoning for two things. We use proportional reasoning to make conceptual arguments in writing. And so some of the free response questions on the AP test are what they call a short answer, paragraph length response, where you just are given a problem and you will have to make an argument about that problem by writing a paragraph. Or we'll use it to perform calculations concerning relationships between variables. Now, I'm going to get into much more detail about that second one here in a couple minutes, but it's important to realize that when we say here, perform calculations concerning relationships between variables, we're not talking about like actually solving for a number. We're talking about seeing how something will change. And I think a lot of you will recognize and remember that you've done this quite a bit already in the first physics class you took. But it's important to realize that what we mean when we say that is not just like solve for an answer. And so the main point here is that this is going to allow us to make arguments by citing one main principle, as opposed to discussing each aspect of the problem individually. And so it's going to allow us to see what affects the variable in question immediately and what doesn't. And this is something that I've talked a lot about this year so far. Because a lot of this test is about explaining, you want to make sure you focus your explanations only on the issues that matter and not necessarily about the things that don't. And of course, the big question as we go through this is, how do you figure out what really matters and what doesn't? And the way that you tell that is by looking at the relationships described in the equations. So the first thing we'll say here is that there are two types of proportional reasoning problems. The first kind is problems that are asking how one variable will change given a change in another variable. And these, I think it's fair to say, are the more basic kind of problem, because they're basically just going to ask you if another variable increases or decreases, then what's going to happen to some other variable in the equation. And you'll be asked whether it increases, decreases, or remains the same. The way you'll figure that out is, of course, by looking at the equation. And the second type of problem is a problem which is going to ask you how or by what factor one variable will change given a change in another variable, which is going to be changing by some other factor. And so they're going to say, like, if this thing doubles, what happens to this other variable? And the way that we're going to use that is by using equations and actually plugging these factors into those equations. Now, this isn't going to give you an actual numerical answer because we won't know the value of all of the variables in the equation. We're just going to know how they're changing. And so the main technique that we use to answer this question of how these variables will change and by what factor they'll change by is a technique that I have always referred to as the 1-1-1 rule. And so what we're going to do now is we're going to take a look at what both of these kinds of problems are going to look like and how we can go about answering them. So to start this off, I think it makes most sense to talk about A, a simple equation, and B, an equation that you're definitely already familiar with and that you've seen multiple times. And so for the purposes of this discussion here, at least to start this out and explain how all this works, we're going to describe all this in the context of Ohm's law. I'm sure you remember this because you should have seen this in shop now multiple times and in honors physics, but Ohm's law is the equation that relates the voltage in a circuit to the current and the resistance. And the reason why we're talking about all of this in the context specifically of this equation is I think it helps to get a number of points across about the other equations that we're going to use for acceleration due to gravity. And so the first point that we want to make here is that when you're answering these kinds of questions, you want to pay very close attention to basically what the dependent variable is or are, depending on if there's more than one of them, and what the independent variables are. Because in certain equations, as you'll see when we get to the acceleration due to gravity problems, you can only change some quantities by changing the value of other quantities. And so you're not going to be able to talk about directly changing some of these quantities because they are dependent on changes in other quantities. And so Ohm's law is a perfect equation to kick this off for, because notice if we solve this equation for each of the variables, we get a different looking equation. And I think the main thing that we want to say here, which is going to inform us when we get to these acceleration due to gravity problems, is that certain variables can only change due to changes in other variables. And so now we want to go through all three of these and think, which one of these variables can you change without having to change any of the other variables? And so the first thing we can say is that the voltage in a circuit can be directly altered. In many cases, when you're doing in physics a circuits experiment, you will have a power supply with a voltage knob on it. And so you can just turn the knob and alter the amount of voltage. Now, the resistance in the circuit is set by the resistor. So unless you change the resistor in the circuit, which is not going to happen if you just turn the voltage knob, that means the resistance in the circuit is going to be constant. So the resistance we'll say is set by the resistor. And so this won't change. It'll be constant, in other words. And so in the context of like an independent or a dependent variable, the resistance doesn't really fall in either of those categories because it's just going to be constant in these problems. If we're assuming that we're keeping the circuit at a constant temperature and it's just this particular resistor, the value of its resistance won't change. The voltage can be directly altered. And so what that tells us here is that the current depends on the values of the voltage and the resistance. And so if we're talking about which of these is the dependent variable, that's going to be our current. And so in terms of thinking about how we can use this to answer the types of questions you're going to get on proportional reasoning, this middle version of the equation is going to be the most appropriate version of this equation. And so what we want to do here is take a look at that version of this equation in a little more detail. What's nice about this form of this equation, number one, is it is written in the form of a fraction, which gives us a sense of how these equations can show you a range of relationships. And so the first thing we'll say is that looking at this equation, we see that the voltage is in the numerator and the resistance is in the denominator. And I'm sure this is review for a lot of you, but we might as well just go ahead and discuss it here. Variables that are in the numerator, which in this case is the voltage, are directly proportional, which means as one variable increases, the other one is going to increase as well. So when this equation is solved for the current, because the voltage is in the numerator, it tells us that the voltage is directly proportional to the current, or in other words, the voltage is directly proportional to the current, whichever way you want to look at it. And so we can say here two things. The first we can say is that if we graph these quantities, then the graph is going to show a direct relationship, so a straight line. And the other thing I want to say about this, just before we move on to the resistance, is that the way we are going to write about this when we are writing explanations is we're going to write about it like this. And so when two variables are directly proportional, we use the Greek letter alpha to show their proportionality. And so this symbol alpha means is proportional to. And we can say it really means it's directly proportional to. And since that's something we're definitely going to want to mention in these explanations, it's definitely something that we're going to want to write down. And so this symbol alpha here tells us that those two variables are directly proportional. On the other hand, the resistance is in the denominator, and so we can say variables like the resistance here that are in the denominator are inversely proportional, which means as one variable, like the resistance, increases, then the other variable, in this case the current, will decrease. And so then the first thing we could say about that is if you graph them, and so if we have the resistance on the x-axis and the current on the y-axis, the graph would look like this, showing that as the resistance gets bigger and bigger, the current is going to get smaller and smaller. And the symbol that we're going to use for inversely proportional is actually going to be the same. And I want you to think about this for a second. There is no symbol for inversely proportional. And so notice we are going to say, again, the current is directly proportional to something. And so I want you to take a moment to think about this. If we are saying the current is directly proportional to something, but the current and the resistance are actually inversely proportional, how are we going to write that? We really only have one possibility, and that is to say the current is directly proportional to the inverse of the resistance. And so when we show this like this, that something is directly proportional to 1 over a variable, it means that the first variable is inversely proportional to x. And so this basically covers the first example of the kind of proportional reasoning question we are going to have to look at. There could be a problem, and you'll see this when we get to circuits, that's talking about a circuit, and they're going to ask you what happens to the current if the voltage increases. And your job is going to be to say, since they are directly proportional, and again, you're going to say that like this using the alpha notation, that because those two variables are directly proportional, if you increased the voltage, then the current would increase. Of course, they could also ask you about what would happen if you increase the resistance, and you would argue it as we've shown on the bottom. It's important to remember, though, and I want to emphasize this because we are going to be using this a lot this year. When variables are inversely proportional, we use the same notation that we use when they're directly proportional. Rather than saying they're inversely proportional with a new symbol, we just say it's directly proportional to the inverse of that quantity. And it's important to realize that actually makes pretty good mathematical sense, because if we plotted the current versus the inverse of the resistance, 1 over R, we would actually see a straight line on the graph, like we do for the graph of voltage versus current. And so when variables are in the numerator, when the equation is solved for one variable, it means that variable is directly proportional to all the variables in the numerator and is inversely proportional to all the variables in the denominator. It's also important to say that you could see that any of these variables are squared or square rooted, frankly, for that matter. And if that's the case, then you just include that in your explanation. The only difference is how the graph would look. If it was directly proportional to something squared, then it would just change the shape of the graph. Or if it was inversely proportional to something squared, instead of curving down like this, it would just curve down steeper and faster. And that brings us to the second kind of problem, where instead of being asked how a variable is changing, whether it's increasing, decreasing, or remaining the same, you are asked specifically how one variable is going to change given the factor by which another variable changes. And the way that we're going to do that is by using a process I refer to as the 1-1-1 rule. And the 1-1-1 rule is a little mathematical technique that we can use to plug factors by which certain variables in an equation change to see by what factor the other variables in that equation will change. So what I think we should do here is just write down the steps. Then we'll go through a number of examples, and then I'll give you a couple to do on your own. So for the 1-1-1 rule, there's 4 main steps. The first thing that you do is you identify the factor by which the variables of interest are changing. They are not going to say in these problems, this thing changes by a factor of 2. Still, they're going to use words that make it easy to identify the factor. They're going to use words like double, triple, halved, quartered. And so you just write down the number associated with that word. If it's doubled, it's 2. If it's tripled, it's 3. If it's halved, it's 1/2, and so on. Step 2 is to write down the original equation for the quantity you're being asked for. And so if they say, what happens to the current if the voltage doubles, you write down the equation for the current, because they're asking you what happens to the current. For step 3, you plug in the factors that you identified in the beginning into the equation. And then for step 4, you pull out the whole numbers and you simplify. There's not a whole lot to this. Take a second to pause this video and here, write that down. And when you hit play, we'll move on. Okay. So let's say you had an example like this. It said, what would happen to the current in a circuit if the voltage in the circuit was tripled? Now, the first thing they're telling us here is the voltage in the circuit was tripled. We have no idea what the voltage is now, and we have no idea what the voltage was. All we really want to show here is that whatever the new voltage is, it's 3 times the old voltage. And the way we do that is by using the symbol prime, which is kind of like an apostrophe. And if you were in Miss Neron's class in honors physics, you probably did this as well. And so what we're writing here is V prime, which means the new voltage is 3 times the old voltage, which we're just going to give the symbol V. So V prime, the new voltage, is equal to 3 times the old voltage because it was tripled. And because we're looking for the new current, and again, the way we denote new is with this prime, we write I prime is our unknown. Step 2 said to write down the original equation for the variable we're looking for. And so we write down I equals V over R. Now, it's important to realize here what we're saying by not including any primes in this equation is that whatever the old current was, again, we don't have to know it to answer this question, it was equal to whatever the old voltage was divided by whatever the old resistance was. And so now that we want to find the new current, we write I prime, and then we do as step 3 said, which is to plug in the factors we identified in step 1. And so the new current is going to be 3 times the old voltage over, and then we have to ask ourselves, how does the resistance change? And because the resistance doesn't change, we just plug in R. Now, if you're asking yourself, why is this called the 1-1-1 rule, is because if the resistance doesn't change, and this is true for any variable that doesn't change, basically we just plug in a 1 for that. Now, you're never going to see me write the 1, because everybody should know that 1 times R is just R, and so we just leave it as R, but that's where the name comes from. If something doesn't change, we just plug in a 1 for that. And notice the last step here was to pull out the whole numbers and solve. And so notice we're going to have I prime equals 3, and once we've pulled that whole number out, what we're left over with is V over R. And here's the whole point of this. Notice we have the number 3 times V over R. And V over R is what we said the old current was equal to. And so the way we finish this off is just by writing I prime, the new current is 3 times I, the old current. And that's it. Now, if they told us the original current was 9, then all we would have to do is plug that in for I, and we would get 3 times 9 is 27. We don't have to know the voltage. We don't have to know the resistance. All we have to know is the factor by which the voltage changes. And if we know that the voltage in a circuit triples, then no matter what the original current was, the new current is going to be 3 times larger. Let's go ahead and look at another example. In this example, it says what would happen to the current in a circuit if the resistance in the circuit was doubled. And so we go through the same steps. R prime, the new resistance, is 2R, the old resistance. And we're looking for the new current, which is I prime. The equation for the current is voltage over resistance. And so to plug in for the changes here, we write I prime equals V. Again, because that doesn't change, we could plug that in as 1V or just leave it as V. And then we divide that by the change in the resistance. So we plug in 2R. And so here now, the number we have up top was a 1. The number we pull out from the bottom was a 2. And then we leave behind all the variables, which was V and R. And again, because V over R is what we said the old current was equal to, we finish that one off by writing I prime is 1/2 I. And that answer, I hope, should make sense. Because we said before, if we look at the equation for current, we see that the current is inversely proportional to the resistance, or is directly proportional to the inverse of the resistance. Same thing. And because the current is inversely proportional to the resistance, an increase in the resistance should yield a decrease in the current. That's what it means for two variables to be inversely proportional. Similarly, notice when the voltage increased, we saw an increase in the current, and that's because according to the equation, the current is directly proportional to the voltage. And so we saw an increase in the voltage yield an increase in the current, which is what it means for two variables to be inversely proportional. All right, now we've covered all of the possible examples, but I just want to go through one more very quickly because it tends to be tricky for some people, and since this is a thing that I normally see students make mistakes with in the beginning, I just want to make sure we take a second to discuss it. And so this problem says, what would happen to the current in a circuit if the resistance in the circuit was quartered? And the whole reason why we're talking about this is the very last step. So it says here the resistance in the circuit was quartered. So that means R prime is 1/4 R. It's decreased. And now you should be asking yourself the question, what should happen to the current if the resistance decreases? Well, they are inversely proportional. So you should expect what we should see here. And so we're looking for our new current, and the original current was V over R. And so that means our new current, I prime, is going to be V over 1/4 R. And so when we pull out our whole numbers, we pull a 1 out of the top, and we pull a 1/4 out of the bottom. And then we put V over R. And the whole point of this discussion was that you have to make sure when you have a fraction in the denominator that you pull the 1 out of the numerator first, because you have 1 divided by a fraction. Now, if you remember that these variables are inversely proportional, so a decrease in the resistance should cause an increase in the current, then hopefully you'll remember that the current is supposed to get bigger. And if you accidentally forget to pull the 1 out of the top and your answer is just 1/4, you will catch your mistake. But the whole point of this is that you only see this, or at least obviously, if you pull the 1 out of the numerator, because then here you have 1 divided by 1/4, and that's 4. And of course, V over R is our original current I, and so we have the current quadrupling here. Again, whatever happens to the resistance, effectively the opposite happens to the current because they're inversely proportional. Okay, so now that we've discussed the basic idea here, what are these questions going to look like? And as I'm sure you saw, there was a worksheet attached to the post with this video in it, where we have a bunch of questions where we're going to be able to apply some of these things. But first, I want to just take a quick look at a question from the packet. So this question in the packet is on page 16. It's number 16. And it says here, you throw a small ball upward and notice the time it takes to come back. If you then throw the same ball so that it takes twice as much time to come back, what is true about the motion of the ball the second time? And there are 4 choices. The first thing I want you to do here is take a moment to look at all these answer choices, and I want you to pick first the answer choices that are definitely wrong and make no sense. And then we'll go over those first. And then now that we have it winnowed down to a smaller number of answer choices, we'll be able to pick the appropriate one. Go ahead and pause this video here. When you've eliminated some answer choices, hit play. Okay, so answer choices that definitely make no sense. C says it had twice as much acceleration on the way up as it did the first time. No, it did not. The acceleration due to gravity is 9.8 meters per second squared. And that's true on the way up and the way down, both times. That is definitely wrong. C is out. And choice D is wrong. This is really important to remember. The ball does stop at its highest point. That is a fact. But just because the ball stopped does not mean it has 0 acceleration at the highest point. That is wrong. And so D is out. And now you have a choice between A and B. I want you to take a couple minutes to pause this video here. And I want you to do 2 things. The first thing I want you to do is I want you to pick your answer choice. It's A or B. We've winnowed it down to those 2 choices. Pick one. The first thing I want you to do is pick. And the second thing I want you to do is prove why that answer is correct. And when you hit play, we'll go over it. Okay. Now, the answer to this question is A. And what I want to do here is sort of focus you in on a couple of things you should be thinking about, and then we'll go over the proof. So the first thing you should be thinking about when you see a question like this, that you throw the small ball upward and you notice the time it takes to come back, and then you throw it up again and notice it takes twice as much time, is you should be thinking, what would make the ball take twice as much time? What can you change about the ball to change the time? And this goes back to what we were saying about Ohm's Law. You can't just like turn the time knob and make the ball stay in air for twice as long. You can't change the acceleration due to gravity on the Earth because that number is constant. The only thing you can change is the speed. The initial velocity of the ball is the only thing that can be changed. And so when I'm looking at the answer choices, because A is an answer choice that mentions changing the initial speed, that's what I want to look at. Now, B is talking about the ball traveling an upward distance that is twice the distance of the original toss. It's important to realize to make the ball reach a higher maximum height, you can only do that by changing the initial speed. So the first thing I want to do here is I want to look at how the initial speed affects the time. And so they told us here in the answer choice the initial speed was twice the speed it was originally. So that means your V naught prime is 2 V naught. And we want to see how that's going to change the time. Now, the other thing that's important to remember is that to find the time to the max height here, the final velocity is going to be 0. And so what we want to do is we want to use an equation that's just going to directly compare the time and the initial speed with nothing else messing this up. And the way that we do that is by using the final velocity equation, Vf equals V naught plus AT. Because notice, besides the acceleration, which is a constant, and the final velocity, which is a constant, the only other variable in there besides the time, which is what we're trying to see how that changes, is the initial velocity. And so to solve this for the time now, we get negative V naught over A. And of course, this is just negative here because the acceleration due to gravity is negative, and those are going to cancel. And so we'll plug in T prime equals negative 2 V naught over A. And now we have to pull out our whole numbers. So we have 2 times negative V naught over A. Notice I take out the 2 here, but not the negative sign, because the negative sign was in the original equation. It's important to realize when I write in that step 3, pull out the whole numbers, or I guess that's step 4, pull out the whole numbers. What you want to leave behind in these parentheses here is the original equation. And since the original equation was negative V naught over A, that's what should be left behind in the parentheses. And so now that we have the original equation left behind in parentheses, negative V naught over A, we just replace that with the term it was equal to, which is T, and we get that T prime is equal to 2T. And so that tells us that when we double the initial velocity, we double the time. And that's because, according to this equation, the time is directly proportional to the initial velocity. And since the time is directly proportional to the initial velocity, if we throw the ball at twice the initial speed in the second experiment, twice as much as we did in the first experiment, it makes the answer choice A. But of course, choice B is a pretty compelling one. It says here it traveled an upward distance that is twice the distance of the first toss. So what I'd like you to do now is I would like you to answer the following question. If the initial velocity of the ball is doubled, which is what would have to happen in order for the time to be doubled, by what factor is the maximum height of the ball changed? Take a second to work that out here. And I'm going to say one more thing before you do that. It's very important for everybody to remember for this one, you want to make sure you pick an equation where only the variable of interest, in this case the velocity, changing is going to affect the maximum height. And so you want a one-to-one correlation here. You don't want any other variables to interfere. All right, take a minute to pause this video here, work that out, and when you're finished, hit play. We'll go over it. Okay, so this question here says if the initial velocity of the ball is doubled, which makes the time doubled, by what factor is the maximum height of the ball changed? So let's take a look at this one. So we're told and we know, because this is what we solved for in the beginning, that the initial velocity of the ball, the new initial velocity of the ball, is 2 times the old initial velocity of the ball. We know, of course, when this thing gets to its maximum height, the velocity is 0. And we're now looking for how that affects the new maximum height of the ball. And so the important thing to realize here is when you're picking this equation, the equation you're going to use here, you want to make sure that the equation you're using is only going to show the maximum height of the ball being affected by the change in the initial velocity. And for that, you want to use the time-independent equation. Now I'm just going to stop here to say, if you used the displacement equation, it can work, but it's a little more complicated, and so we'll talk about that after. But this is certainly the best equation to use, because once you recognize that the final velocity is 0, and you solve this for the displacement delta x, you get the displacement is negative v naught squared over 2a. And since a is a constant, the only variable which can affect the size of delta x is v naught. And so to finish this one off, you write delta x prime is equal to, and now we plug in for our changes. The negative sign is on the outside, and so we have 2 v naught squared over 2a. And I'll write this over here now. That would give you negative 4 v naught squared over 2a. And this one's a little tricky, but it's important to realize, remember, we said when you pull out the whole number, what you want left over inside the parentheses is whatever you had in the original equation. So that would be negative v naught squared over 2a. And so this calculation here shows us that delta x prime is 4 times the original delta x. So what that means is, looking back at this equation here, because that equation tells us delta x is directly proportional to v naught squared, a doubling of the initial velocity gives you 4 times the maximum height. It's because of that squared relationship. And so before we move on to show how this works with the displacement equation, I just want everybody to take a moment to write this down. Note, while any valid or relevant equation can be used for 1-1-1 rule style problems, the best equation is the equation that shows the relationship between the variable of interest and one other variable. Other equations can be used, but you'll have to account for how all the other variables change. And so we'll get to this in a second here, but I'd like you to go ahead and pause this here, copy that down, and when you hit play, we'll go over how to do it with the displacement equation. Okay. So what's tricky about doing this with the displacement equation is that once you write it down and you realize that nothing goes to 0, in this equation, there are 2 variables that could affect the size of delta x, and that would be v naught and t. The only variable in this equation that's constant is a. And so what you need to keep track of then is the fact that the new initial velocity is twice the initial velocity, and that when you double that initial velocity, you also get a doubling of the time. And both of those are going to affect the value of our delta x prime. And so, again, it's the same kind of procedure here, but it just gets a little more complicated, because notice when we write our first line for delta x prime, we have the initial velocity doubled, so we write 2v naught, then 2t, then plus 1/2 a, and then because the time doubled, we write 2t, close it up in parentheses, and then square it. And so when we do the math here, we get delta x prime equals 2v naught times 2t is 4 v naught t. And then we have plus 1/2 a. And then when we take 2t and we square it, notice that's 2t times 2t. So that's 4t squared. And so to perhaps make this a little more obvious, we can rewrite this like this. 4, and then in parentheses, v naught t, plus 4, and then in parentheses, 1/2 at squared. And notice, because both of these terms have a 4, we have to factor it out. And then we have each of these terms here, v naught t plus 1/2 at squared. And so notice it still works the same way. Now that what's in the parentheses is the original equation, we can just rewrite this as delta x prime equals 4 times delta x, giving us the same result as the time-independent equation. But the displacement equation is an equation for these problems you're almost never going to want to use, because it's showing you the relationship between three variables, delta x, v naught, and t, which can all change if the initial velocity is changed. And so your best bet is going to be using the final velocity equation, v final equals v initial plus at, or the time-independent equation. And so this note here is very important. And with that, that brings us to the problems on the sheet. So if you go to the main post for today on Google Classroom, you will see a sheet entitled AP Physics Tippers, Acceleration Due to Gravity. And there are 4 problems on this sheet. I'd like you to start with the first one on the sheet, B1 RT15. It says the model rockets depicted below have just had their engines turned off when they're at the same height. All of the rockets are aimed straight up, but their speeds differ. And then it says, although they are the same size and shape, the rockets carry different loads, so their masses differ. The specific mass and speed for each rocket is given in the figure. Rank the maximum height the model rockets will reach. So what I'd like you to do here is go through and rank the heights. And when you get to the explain your reasoning part, and this is basically going to be true from now until the end of the year, I want you to think about how you can explain this using the concepts we discussed at the beginning of this video. How can you explain this using proportional reasoning? Take a couple minutes to pause the video here and answer this question, and when you hit play, we'll go over it. Okay, so as we see in this problem here, the mass and speed for each rocket is given in the description, and the question is asking to rank the maximum height the models will reach. Well, according to the equation that we can use to solve for the maximum height of one of these rockets, we see here that the maximum height is directly proportional to the square of the initial speed. And that's really the only thing that determines the maximum height. And so since B has the largest initial speed, it will have the largest maximum height, then A, and then C and D have the same initial speed, and so they'll reach the same height. And so that would make your ranking B is greater than A, which is greater than C, which is equal to D. And what you would say about that is pretty straightforward. You would say here, according to the equation, delta x equals negative v naught squared over 2a, the maximum height reached by the rocket is directly proportional to the square of the initial velocity. And of course, you could say that, as we said before, by writing delta x and then the Greek letter alpha, and then v naught squared, which means the larger the initial velocity of the rocket, the larger the maximum height will be. And that's really it. But of course, since they're giving you additional information in this problem, mainly the masses of each rocket, that is an important thing to address as well. And since the equation says nothing about the mass of the rocket, because that has nothing to do with it, it doesn't hurt to just, in one sentence, say the mass of the rockets has no effect on their maximum height. And that's it. So your explanation should look something like that. Right, now for the next one I'd like you to look at is B1 WWT24. It says a ball is thrown straight upward and falls back to the same height. A student makes this graph of the velocity of the ball as a function of time. What, if anything, is wrong with the student's graph? Take a second to look at this one, write an explanation, and when you hit play, we'll go over it. Okay, so notice this one wasn't really a proportional reasoning one as much as it was just a question about applying understandings about the motion of an object thrown straight up in the air to a graph. And so this one is showing you a graph of velocity versus time, and it's saying if there's anything wrong with this graph, explain the error and how to correct it, and if the graph is correct, explain why. And so starting from the beginning, notice here, the first thing that happens to this graph is that it shows the object starting with a positive velocity. Remember, the sign convention is very important for these problems, and so the fact that the velocity is positive tells us that the ball is going up, which it should be, and so that's correct. And notice here the slope of the graph is constant and negative, showing us that the object has a constant and negative acceleration, which it should, and so that's good too. And then the velocity eventually gets to 0 in the middle of the trip, which it should, because it stops when it gets to its maximum height. But the part of this that's wrong is at the end. And so the important thing to realize here is that this graph is wrong in the second half. Since the ball is stopped at its maximum height, the downward acceleration due to gravity is going to cause the ball to fall back down to the ground with a velocity which increases in the negative direction. This means the whole second half of the graph should be below the x-axis. Additionally, the acceleration due to gravity is constant, so the slope of the graph should be constant and negative the whole time. And so to fix this, we can get rid of this part, because that's wrong, and show this line continuing with the same constant and negative slope. And so we can say here, the velocity increases in the negative direction. That's a negative sign. With a slope of negative 9.8 meters per second squared. If any part of what you wrote was missing any of that, I suggest you take a moment here to pause this and write that down. And when you're ready to move on, hit play, and we'll take a look at another one. All right. Let's take a look at another one on that sheet. This one's now on the back. It says B1 WWT32. It says a student throws a ball straight upward. A friend times how long it takes the ball to reach its maximum height. And it says the student predicts faster things take less time. If I throw the ball faster, it will reach its highest point in less time. It says, what if anything is wrong with the statement? If something is wrong, identify it and explain how to correct it. If the statement is correct, explain why. Take a couple minutes to look this one over. Write an explanation based on your conclusion about this student's reasoning. When you hit play, we'll go over it. Okay, so this student is saying faster things take less time. If I throw the ball faster, it will reach its highest point in less time. Now, what's important to think about here is what equations do we have about the relationship between the time and the initial velocity? Well, as we saw earlier, we could use this equation. But if we use this equation now, we have three variables, v naught, t, and delta x, which could change. And so that means this equation is probably not the best equation to use to do that. The best equation that gives us the relationship between the initial velocity and the time is this one. And we have to think about what this equation says. This equation says that the time it takes the object to get to the maximum height is actually directly proportional to the initial velocity. And so that would be the main structure for your reasoning. You just look at what the kid said. The kid says if the initial velocity is larger, the time should be less. And this equation directly contradicts that. So that's definitely something you want to talk about. But you also want to try to take the opportunity to confront what it is the student is thinking. And so you have to ask yourself the question, when do you see faster things taking less time? Like, where is that idea coming from? And where that idea comes from is this equation. But there is a key thing that this equation assumes when you say the time is inversely proportional to the velocity, so that if you go faster, the time is smaller. And what that reasoning assumes is that the distance is fixed. And according to the equation that we developed earlier, the relationship between the initial velocity and the max height, if the initial velocity increases, the maximum height increases as well. And so an answer could look something like this. According to the equation t equals negative v naught over a, the time is directly proportional to the initial velocity, meaning a larger initial velocity will produce a larger time of flight. Faster things only take less time if the distance is fixed. However, according to delta x equals v naught squared over 2a, negative v naught squared over 2a, the max height is directly proportional to the square of the initial velocity, meaning a larger speed will also produce a larger maximum height. When you're confronted with reasoning in these problems that's just totally ridiculous, it's probably not a bad idea for you to just ignore it. It's wrong. But when you're confronted with reasoning that sort of makes sense and is actually based on some reasonable physics, you want to confront it head on and provide a compelling explanation for why that's wrong, which in some sense will be further evidence of why what you're saying is correct. And the way to do that in this problem looks a little something like this. Take a second to pause this video here, write that down, and when you hit play, we'll take a look at one last problem before we wrap this up. All right, let's just look at one more before we wrap this up for today. Last problem I want to look at is the last one on the sheet. It's B1 SCT25. It says ball thrown upward, graph of speed versus time. And it says here, a ball is thrown straight upward and falls back to the same height. The student makes the graph of the speed of the ball as a function of time. Three students who are discussing this graph make the following contentions. And they give three arguments given by three different students. And so I want you to go through the three of their arguments Pick which, if any of them, do you agree, and if you agree with none of them, then you select none of them, and then you explain the resolution to the argument that these three students are having. Take a couple minutes to pause this video here and work this one out, and when you're finished, hit play. We'll go over it. Okay, so looking at the arguments made by the three students, they say some things that make sense. Akira says, I don't think this can be correct because the sign of the acceleration changes on this graph, but the acceleration on the ball will be constant. So notice she's pointing out here that the sign of the slope is changing from the first part to the second part, and correctly indicating that the acceleration of the ball should be constant, which it is. Bert says, no, I don't think this is right because it is only showing what happens to the speed, which will decrease to 0 at the top and then increase as the ball falls. Since the slopes for both segments are the same except for the sign, that means the acceleration is constant. It's pretty compelling. Catalina says, this graph makes sense to me because it shows the speed decreasing on the way up. But I disagree with Bert because I think this means that the acceleration is also decreasing until the ball gets to the top and stops. Then both the speed and the acceleration increase as the ball falls down again. Okay. So the first thing that we should note about these arguments is that answer about the acceleration also decreasing until the ball gets to the top and stops is dead wrong. The acceleration is constant the whole time in magnitude and direction. And that's manifested on the graph by showing straight lines which indicate a constant slope. Now, the resolution to this argument is really picking out who between Akira and Bert are correct. And the answer here should look a little something like this. Bert is correct. Speed is a scalar and thus can't be negative. And so we can say here that the speed has a negative slope. The graph of speed versus time has a negative slope on the ball's way up, indicating that it is slowing down, and a positive slope on the way down, indicating an increase in speed. The slope of a speed versus time graph represents the magnitude of the acceleration, and so the acceleration is constant. And so typed out correctly should look like this. Speed is a scalar, and thus can't be negative. The speed versus time graph has a negative slope on the ball's way up to the maximum height, indicating it's slowing down, and a positive slope on the ball's way down from the maximum height, indicating an increase in speed. The slope of the graph of speed versus time is the magnitude of the acceleration. And so this graph gives no information about the sign of the acceleration. It just shows it has a constant magnitude. And that's really it. There's not a whole lot else they can ask you conceptually about objects thrown straight up in the air. The main thing we want to emphasize here before we go is just that this style of question using proportional reasoning, as was shown in the example from the packet and the first and third question on the sheet, are going to be the kinds of questions you'll be seeing in every single topic for the rest of the year. So if you have any questions about that, make sure you ask. And that's it for today. Have a good one, everybody.